Hello, everybody. So today we're going to talk about some important distributions which come up in the context of probability theory. Okay, so we're going to start out by giving a brief review of what a distribution is in the context of probability theory, and then we'll split up the distributions we're going to talk about into two broad categories, which are called discrete probability distributions and continuous probability distributions. Okay, so as a very brief review of probability theory, we start out with a probability space. So this is going to be a set along with a collection of subsets obeying certain axioms. Namely, they should be a sigma algebra. And then we have a particular function from a subset of these spaces to the interval 0, 1, which obeys the following axioms. So in particular, the probability of the MC set, which is contained in this collection of subsets, should be 0. And the probability of the union of a disjoint collection of sets AI should be equal to the sum of the probabilities, right? So this is just the basic notion of what a probability space is. But then if we want to add additional data, namely what's called a random variable, which is a function from the original set to the real numbers, then we can talk about this concept of a distribution of a probability space. So this is just a genuine function that you'd typically manipulate in something like a calculus class, which follows from essentially taking the inverse image of a set, which will be something in the probability space, and then taking the corresponding probability of that set. Right. So just to reiterate, once we're dealing with distributions, we can use techniques that we're familiar about manipulating functions from calculus and whatnot. But it's good to keep in mind that there's all this machinery about the probability space that is underlying all of these computations. Right. So in particular, what needs to be true for this to be a probability distribution is that the total probability should be equal to 1. Right? But we also may be interested in what are called moments of probability distributions. So in what we will get to is the context of a continuous distribution, the total probability being 1 means that the integral over all space of P, which is the distribution, should be 1. A moment means we put additional powers of X into the integrand, right? So in particular, the kth moment means we take the integral over all space of X to the power of K times the probability measure. So the expectation value of X, which is basically the mean, is just we have just a power of X in there. So that's the integral over all space of X px dx. Another one which we may be interested in is what's called the variance. So that's the expectation value of X squared. So we put an X squared in the integrand minus the expectation value of X, all of that squared. You can express it in that form. But more generally, we can encode all of this information about the moments of the distribution in terms of what's called the moment generating function. So that's given below as to how we extract from the moment generating function, which is the integral below a particular moment. So basically, this integral can be thought of as a function of alpha, and then we differentiate the integral with respect to alpha k times, and then we set alpha equal to 0 to recover the kth moment of our distribution, right? So this is essentially relying on the fundamental theorem of calculus as well as how derivatives of the exponential functions work. But this is a nice way to package all of the moments of a distribution in terms of one particular integral. Right. So now we're going to specialize into two broad classes of probability distributions. So this will be discrete and continuous. So in the discrete case, we can have a finite number, or we have a discrete spacing between possible outcomes. So if the outcome is like, say, x is equal to 1, we could have x equals 2, x equals 3, but there needs to be some spacing between these things, right? So in this context, we have what's called a probability mass function, and we're going to be dealing with essentially discrete sums in this case. So the sum over all possible outcomes should be 1, but in the continuous case, right, these are not going to be discretely separated outcomes. These are be continuous. So we'll be dealing with what's called a probability density function. And in these types of computations, we will be doing integrals, right? So the total probability being 1 means we integrate over all space, and this should be equal to 1. Right, so we'll start out going through some discrete probability distributions, and one of the most important ones is what's called the binomial distribution. So the interpretation of this is that we do n trials. The probability of success of a trial is p, and the probability of failure is 1 minus p, right? So those are the two possible options. The total probability is 1, and we want to know the probability that we have x successes out of these n total trials, right? So why does the expression above make sense? The point is we need to choose which of the x, given that it's true that we have x successes, we need to choose which of the x trials are the successes out of the n total. So that's what the combination out front comes from. Then we need the probability of x successes. So we're assuming that these trials are going to be independent. So that will be just x powers of p for the successes. And then the failures, there will be n minus x of those failures, and they each have probability 1 minus p. So putting that all together, we get the expression above. Then by direct computation, we can get the expectation value of x and the variance of x associated with these. The expectation value of x expression makes sense given that we would expect, given n total trials with a probability of success p, that the product should be the number of expected successes, right? So that would be n times p. Another thing maybe to note about this is that the fact that the total probability of this distribution is equal to 1 is a consequence of the binomial theorem. And also the moment generating function at the bottom takes the form p e to the t plus 1 minus p all to the nth power. Another distribution which comes up quite frequently in the discrete case is what's called the Poisson distribution. So this is typically used to model the probability of rare events. So x could be 0, x could be 1, 2, 3, et cetera, and the probability that it has any of those values is given by this expression here. So the fact that the total probability is equal to 1 in this case is a consequence of the series definition of the exponential function, right? And another thing which is very notable about this distribution is that the expectation value of x and the variance of x are both this parameter lambda, which is involved in the distribution. And then in this case, the moment generating function is e to the lambda e to the t minus 1. Another discrete distribution which comes up quite a bit is what's called the geometric distribution. So this is the probability that we get our first success on the x trial, right? So the reason that this is the expression for that is we assume we have independent trials. The probability of success is p. The probability of failure is 1 minus p. So if our first success is on the xth trial, then that means the previous trials were all failures. So we need them to be 1 minus p to the x minus 1 because there are x minus 1 previous attempts. So those are the failures. And then the last success has probability p. So we multiply it. All right. The expectation value of x in this case is 1 over p, and the variance of x is 1 minus p over p squared. And then the moment generating function is p e to the t over 1 minus p e to the t. And in this case, the fact that the total probability is equal to 1 is a consequence of the series expression for, essentially summing a geometric series. Okay, so another discrete distribution which frequently comes up, and in which in particular is a generalization of the geometric distribution, is what's called the negative binomial distribution. So in this case, it's reflecting the probability that on the nth trial we have r successes, exactly r successes, and that last success is precisely on the nth trial, right? So we know that the last trial is going to be a success. So we need to select which of the previous trials are going to be successes and which ones are going to be failures. So there's n minus 1 previous trials. There will be r minus 1 successes besides the last success. So that's the combination out front. And then we have r total successes. So that's the p to the r. And n minus r total failures. That's the 1 minus p to the n minus r. Right. So what's notable about each of these other expressions is that they're direct generalizations of what we saw for the geometric distribution earlier. Namely, the geometric distribution has r equaled 1, right? So in particular, this case, the expectation value of x is r over p. the variance of x is r times 1 minus p over p squared, and the moment generating function is p e to the t over 1 minus 1 minus p e to the t, all raised to the rth power. Okay, so now we'll start going through some continuous probability distributions. The most basic one is the uniform distribution. So in this case, each value of x has a constant probability. Every outcome is equally likely. And we'll consider this over the interval from a to b, right? So what that means is that the density is going to be 1 over b minus a over this integral. So in particular, it's a constant. The expectation value of x is going to be a plus b over 2. So if you think about the interval, that's precisely the midpoint, which makes sense. That's how the average should work out. The variance is maybe a little bit less intuitive, but it takes the form b minus a squared over 12. And then the moment generating function is e to the tb minus e to the ta over tb minus a. Okay, and then another important distribution in the continuous case is called the exponential distribution. This is very natural, just takes an exponential dependence like this in terms of a parameter lambda. X is presumed to be positive in this case. The expectation value is 1 over the parameter lambda. The variance is 1 over lambda squared. And then the moment generating function is lambda over lambda minus t. What's important about this distribution is that it's what's called memoryless. This comes up frequently in problems for essentially waiting times for buses. And what's the probability that you'll wait a certain amount of time for the bus to show up and whatnot. And that has to do with the memoryless aspect, which is related to conditional probability. The gamma distribution is a generalization of the exponential distribution where we throw in an additional parameter s. So in particular, the exponential distribution corresponds to gamma with s is equal to 1. So defined over the same interval, it's lambda e to the minus lambda x times lambda x to the s minus 1 over the gamma function for s. So the expected value in this case is s over lambda. The variance is s over lambda squared, and the moment generating function is lambda over lambda minus t, all to the s power. And now the last distribution in the continuous case that we'll talk about is the normal distribution. So this is essentially the bell curve, which comes up very frequently in probability theory, and is also important as a result of the central limit theorem, right? So the form of this distribution is 1 over square root of 2 pi and then there's some parameter sigma, e to the minus x minus mu squared, mu is another parameter, over 2 sigma squared, right? And then this is defined over the entire real line, right? So there's 2 parameters involved here, mu and sigma, right? And the importance of these is that the expected value is going to be mu from this distribution, so that's going to be the mean, and then the variance is going to be sigma squared, right? And then we can get all of the moments from the moment generating function, and that also takes an exponential form. It's e to the mu t plus 1/2 sigma squared t squared. Okay. Thank you very much for listening. I'll be coming up with some more probability theory and general mathematics, mathematical physics videos soon, and I hope to see you then. Thanks.